As we have discussed in our earlier lectures, the objects that we are actually interested in calculating will look like these. This is the vacuum of the theory, and then we will be creating some particles in this vacuum, and the system will evolve from T0 to, let's say, T1, and then we will see if we have some other particle at the point x1. This is what we call the propagator. And then we had also seen that this we can write as a limit. Now this is the empty vacuum. This is the vacuum of the theory, which need not be empty, but this is the empty vacuum, e to the power minus IH T0 minus T. So we say that our system is at the empty state at the time minus T, which eventually we will take to be infinite. And then we evolve it to the time T0, and this will essentially pick up the interacting vacuum. Then we have our phi dagger x0, e to the power minus IH T1 minus T0, and phi of, we evolve the system to time T1, then we check if there is a particle at the point x1, and here we have e to the power minus IH T minus T1. So what we are doing over here is, and after the interaction, after we check, we let the system evolve again to a time capital T, which will again be infinite, and at the time T the system will be in vacuum. And of course there will be some phases. To fix the phases we just divide by E omega. This is the energy of the vacuum, and T minus T, and the overlap with of the vacuum state with the real vacuum of our interacting state divided by squared. Now this here we should actually take some limit as t goes to infinity with a slight imaginary part, so that this imaginary part is actually what singles out the actual vacuum, the minimum energy state of the system. So this is what we need to evaluate. Now let's see how we can express. Let's just look at the numerator for the time, for simplicity, and see how we can express this in terms of our path integrals. Now first I will use the identity. This will be just d phi. I will insert an identity over here and also over here. Let me just write it as the integral x1 t1 phi of x1 t1. Remember that here, although I'm just writing a single integration variable, this is many integration variables at different points of x1 at the same time t1. Phi of x1 t1. This is what I will insert over here, and here I will insert a similar one with x0. So my matrix element actually becomes this one. I have these integrals d phi x1 t1, d phi x0 t0, and then I have the 0 and e to the power minus IH t minus t1 phi of x1. Let me put a hat over here to distinguish this from as an operator. Phi of x1, then I have these states phi x1 t1, phi x1 t1, and then I have the rest of my expression. Well, let me move it down. E to the power minus IH t1 minus t0 phi x, I have this phi dagger x0 now, phi of x0 t0. Let me also put a hat over here, phi x0 t0, and then I have e to the power minus IH t0 minus t 0. Now, I can use the fact that phi dagger, phi hat x1, this is the operator acting on this state, will just give me phi of x1, t1, x1, t1, and similarly over here, this operator acting on this ket will just give me the number phi x0. So if we use also these, we have d phi x1 t1, d phi x0 t0. These are the integrals over the fields at the time t1 and at the time t0, and hence they have each one of these involve an integral over all the values of x1 actually. So we have phi of x1 t1, or in fact let me write it out explicitly. This is d phi x, let me just say xn t1 over all values of xn, and then I have d phi xm t0 over all values of xm. So this is what I actually wrote as d phi x1 t1. So let's continue. Here I have this from the action of this operator on this ket, and here I have this operator acting on this ket, so that will give me phi conjugate x0 t0, and what remains is 0 e to power minus I h t minus t1 phi of x1 t1, phi of x1 t1 e to power minus I h t1 minus t0, phi of x0 t0, and then finally I have phi of x0 t0 e to power minus I h t0 minus t, the empty state. But you see, all of these matrix elements we had already written in terms of path integrals. So I can write all this expression as the integral of the d phi xn t1, d phi xm t0 over xm, phi of x1 t1, phi of x0 t0 conjugate. Now let me write first the measures. Then if from this one over here I have the measure of phi, well, that measure will be actually the product d phi xm tn over all points xm and tn, such that tn will be between t1 and t. So because we are starting at the time t1, evolving up to the time t, and there's also the boundary condition phi of xm t1, phi of xt1 is actually this one. xm t1 will be equal to this state over here. So I mean the notation is a bit confusing, but let's say phi of x1 t1 will be actually phi of x1 t1. This phi of x1 t1 over here is the field in this ket. This phi of x1 t1 is the field over which we are integrating. We are integrating over all these fields. Now from the other one, from this in this matrix element, I will have a similar product. Again over all xm and tn, but this time tn is between t0 and t1. And with similar boundary conditions, the fields I'm integrating over here at the time t0, they should be given by this field in this kit, and at the time t1 they should be given by this field at this bra. And finally I have this third one. In the third one I still have the similar measure, but this time Tn is between here T1 is the smaller one, sorry. From T1 up to T, here we have from T0 up to T1, and here in this measure we start from minus T up to T0. And again, similarly, the fields over which we are integrating will be equal to this field in the bra at the time T0, and they should be equal to the field of the empty state when the time is minus T. And then we have the exponential factors. In the exponential, we have I, L, d4x from the time, let's start from this one, from minus T to T0. Then we have I, integral of the Lagrangian density from the time T0 up to T1. From this corresponding to this integral, and then we also have plus I from T1 to T L d4x corresponding to these integrals over here. But now let's see. Here in these measures, I don't integrate over the value of the fields at the time T1 because they are fixed by these fields over here. But those integrals are just over here. So these two integrals are contain integrals over T0 and T1 which do not appear in these measures. So at the end of the day, I will be integrating over all the field values for all xm and tn, but this time tn is between minus t and t, and t will, keep in mind, they eventually go to infinity. So I'm integrating over all the fields, all possible field configurations that connect minus t to t. And then, well, let me also just write some normalization. So here there is also a normalization which its explicit form will not be important for us. And now we have the exponent I from minus t to t Lagrangian times dx, d4x. And then I also have these terms. Phi of x1 t1, phi star x0 t0. So what we have actually shown up to this point is omega, no, not omega, just the numerator in that expression. This numerator is actually given by a path integral of e to power I s, let me just put minus infinity to infinity, L d4x. And here we have the phi and phi dagger. So in the numerator we have phi of x1, phi dagger of x0. Let me also write the t0s. And t1. Well, I will just use the four-dimensional notation, and from now on, whenever I say x1, it will also contain the time. So this is actually equal to the phi e to power I from minus infinity to infinity L d4x. But keep in mind that we had also shown in our previous lectures that this matrix element is actually equal to the matrix element of the time order product of phi x1 t1, phi dagger x0 t0, e to power minus I integral of v of t dt from minus infinity to infinity. This is in the interaction picture. So basically, we now know how to write these time ordered products in terms of path integrals. Now, just to complete our derivation, note that here we also have the numerator. Well, the numerator, you can actually show that it's identical to the denominator with phi and phi daggers missing. So this term is actually equal to the path integral d phi phi of x1 t1 phi star of x0 t0 e to power I minus infinity to infinity the Lagrangian density d for x divided by d phi e to power I from minus infinity to infinity the Lagrangian density d for x. Well, since we have the ratio of two path integrals, the normalization of the path integral just cancels. And in fact, whatever we have inside these, whatever operator we have over here, they will appear inside the path integral. And when we divide by a similar path integral without any operators appearing, so for example, if this were absent, what we should have is 1, but if these were absent, then here it would be also absent, and we just recover 1.